Welcome to Lecture 2. In our second semester, we will continue in this lecture with the development of the abstract connection between Markov processes and a semigroup on function spaces. We start with basically a definition of the concept that we had already at the previous lecture, which is the concept of a semigroup of kernels. It goes as follows. So if we fix a certain time index z, which in most of the cases is going to be just a non-negative real line anyway, and we consider the collection of all possible differences of time points where the time points are ordered and chosen from this initial time set. So we want to assume actually that the time set I is closed under this operation. Then we can introduce the set of kernels, which we have considered before. So if we assume that this is a time homogeneous transition function, then we can pass to a reduced representation of these kernels by looking at the family of kernels, which then shall be denoted by pi, which are just obtained by fixing the first time at 0 and varying with respect to the second time variable. Then this collection of kernels pi, which is just a subset in a way of these initial family of kernels, is what we call a semigroup of kernels. Namely, it satisfies the following convolution property, which says that the convolution of two kernels for two different time points, s and t, is just as good as if we had taken the same kernel, or from the same family of kernels, the kernel which is associated to the sum of the two time points, which were entering in the convolution before. The proof of this is now pretty easy. So by definition, these two kernels ps and pt, they are these reduced representations for the kernels which are obtained from the two chosen parameters 0s and 0t, and we want to assume that this family of kernels is time homogeneous, so therefore we can write also this as the convolution of the first kernel with respect to or with the second kernel, which is just written as the kernel for two time points, in this case s and s plus t, which are chosen such that the difference between the two time points is the same as in the kernel representation in the first, on the left hand side. And by time homogeneity we know that these two kernels are the same. And then I can use the fact that I was dealing with a transition function which tells me that this consecutive iteration or consecutive convolution of two kernels, where the, if you like, intermediate time point in both sides is the same. It's just the same as if I had taken the kernel right away with the two time points which appear in the extremes of these three time points, namely in this case 0 and s plus t. So hence I have convinced myself that this ps semigroup or kernel with the pt kernel, that this convolution is in fact nothing but the kernel associated to the sum of the two time points. So this semigroup property looks very innocent and simple, and it is, but it's very powerful, and it will be our simple but guiding principle, and we will make use of this a million times. Later we shall understand that this is in fact some sort of an exponential function in an abstract concept. Namely, if you assume for a moment that this ps function is simply an e to the alpha s, then this convolution semigroup property, which is written over there, just corresponds to the functional equality for the exponential function, which says that e to the alpha s times e to the alpha t is of course e to the alpha s plus t. So anyway, this this convolution property here can be understood as a generalization of the functional or characterizing property of the exponential function. And once, in case of the exponential function, we know that we have a function which has this property that f of s times f of t equals f of s plus t, then in one-dimensional analysis we already know that the function f of s must be of the form e to the alpha t. And the only datum, or the only the only datum that is unknown left after we have identified that such a relation holds true is this alpha coefficient. And in a similar way, this is also true for such semigroups, and we will develop a theory now. When the alpha is not a real number anymore, but in our case, alpha will be written as an A, and it will be an operator. And this operator A will be called the generator of the semigroup PT, because once we know that the semigroup satisfies this functional equality, then basically all the definition that we need to identify these P objects are the information about the nature of this A. And therefore, in some sense, all information that is interesting and is needed to characterize these PT is contained in the information about the generator. Well, the previous remark was a little bit ahead of what we are going to do, but we will do that a little later. But before we come to the connection between generators and semigroups, or time homogeneous semigroups, we want to establish the connection, a rigorous connection between the theory of semigroups and our functions, transition functions, and the theory of Markov space, Markov processes once more. Namely, we want to convince ourselves that if we are given a semigroup of kernels, which then generate a transition function, then there is in fact a Markov process which is determined uniquely up to the equivalence of processes in the sense of finite dimensional distributions. And here's the theorem that gives us exactly this. Namely that, assume we have a Polish space which shall be the state space of our Markov process, let I be our time parameter set, and let Pi be a semigroup of kernels in the sense that we discussed just before. So we have in particular this convolution property. Moreover, we fix a starting measure mu, which is a probability measure on this state space. It will have the interpretation of the starting measure of a stochastic process, which we want to construct using this family of kernels, which has the semigroup. Then now comes here the statement. Then there exists a time homogeneous Markov process, which is defined with respect to the same time index set, which is associated exactly with these transition function, which is generated by these, or which is encoded in terms of these kernels, and which has the starting law given exactly by this initial distribution mu. So it says, if you give me a semigroup of kernels, which altogether generate a transition function in this way, then there is a stochastic process, a Markov process, which is time homogeneous and whose transition function is exactly given by this transition function induced from the kernels, where we have the choice or the freedom to make a certain choice regarding the initial distribution. And this process X is unique in the sense of finite dimensional distributions. So if you compare to what we had seen in the past in the theory of Markov chains, there we had a statement like this: if you give me a transition function, a transition matrix to be precise, P, and an inertial measure, then there is a uniquely in terms of finite dimensional distribution, uniquely defined Markov chain whose statistics are exactly described by the iterates of this matrix. And in an appropriate fashion. And this statement here is exactly the same. It's the same kind of assertion, but now in the case when the transition probabilities are not described in terms of powers of a transition matrix, but they are described in terms of this family of transition functions. Hence, it's not surprising that the mechanism of the proof of existence is basically a repetition of the proof that we did for the Markov chains in the time discrete and state discrete situation. However, there's a few more concepts that we shall introduce and use for that, just for the sake of simple notation and for the sake of having some constructions at our hand that we shall make use of also later. So we shall use the following notation when we prove this existence of this process. And if we have a measurable space, then we can consider the Banach space of all measurable bounded functions, which we equip then with the supremum norm. This is a Banach space, as we discussed, by the way, in the last exercise class. And if we have a Markov kernel, so just a transition kernel, on this measurable space, then we can also induce with this Markov kernel an operation on the functions. Namely, we take a function and we use the kernel k to convert the function into a new function. And it does the following. So this new function kf, it's a new function which is a transformation of the initial function by means of the Markov kernel k. If you evaluate this function at position x in state space, this is defined to be the integral of the f function against the kernel measure at kernel position x. So it's the average value of the observable f if you make a one-step transition which starts in x. That's the meaning of this operation. So let me say it again. When you have a kernel and you have a measurable function, then you can use this kernel in order to transform a function by this kernel exactly in this fashion. You take the average value of the function against the kernel measure, which is evaluated at a starting point x. That defines a new quantity, and this quantity depends only on x and e anymore. And since the kernel as a function in x is measurable, this defines a new measurable function. Okay. And in the future, we typically will not make any distinction anymore between the kernel k and the corresponding operation on functions. Of course, the kernel induces a unique operation, and vice versa. Once if you have this operation, then you can recover the kernel by just evaluating this operation on indicator functions f. That will retrieve the measure. So therefore, the kernel and this corresponding operator on functions are the same. Let me say it again. If we have a kernel, we have a map which takes a bounded measurable function and returns a bounded measurable function, and the construction mechanism is like this. So that will be the application of a kernel on a function. This construction generalizes in a straightforward fashion the operation of taking the multiplication of a vector, which is f, against a stochastic matrix k. So the stochastic matrix will be something like a Kij matrix. And what I do here, instead of the continuous integral, I would do an f of j probably operation. That, if I sum over all j, would be exactly the multiplication of the f vector against the matrix k evaluated at position I. So you see that this operation that we have here defined below generalizes the familiar operation of multiplying a vector on a matrix. Now, if we have not only one kernel k, but an entire family pi, which is indexed by I, and if this family of kernels is in fact a semigroup of kernels in the sense that they are stable with respect to convolution, then the corresponding family of induced operators, so for each I or each S and T, we then have such an operator. And then we find that's a statement here. You find that this family of operators constitutes a semigroup of operators, which is to be understood as follows. If you take two time points S and T, and if you evaluate the operation on one of the time steps, pt, on the function f, that gives you a new function, and then you iterate this, or you apply to this new function yet another transformation by means of a second kernel. So what is this here is just the twofold application, or the consecutive application of this kernel transformation of a function by means of two kernels at possibly different times. And what it says is that this is just as good as if you had just done one operation with one kernel, but now the kernel, we have to take the kernel at time point s plus t. So if you compare again to what we know about Markov chains, this is in a way to be understood as the evaluation of an observable after s steps and then after t more steps when we start the Markov chain at position x. And this here would say, okay, the evaluation or the average value of the function f after we do first t steps and then s steps is just as good as if we take just s plus t steps and then do the average evaluation, provided the starting point in both evaluations was the same. So this equality here is characteristic or is characterizing what we shall describe or shall we call a semigroup of operators. So if we have a family, if we have a kernel, we can associate to a kernel an operation on functions. And if we have a family of kernels, which is a semigroup, then the corresponding family of operators are a semigroup again, in the sense that the iterated application of these operations is just as good as if we do just once such an operation, but with the properly chosen time parameter, which here will be just the sum of the two time parameters which entered on the left-hand side. After we have used this notation and we have identified this structure, I shall now come back to the proof of the existence of a Markov process X, which is in time homogeneous, provided we are given such a family of kernels. And the proof here, as I just said, is pretty much the same as in the case of Markov chains. So the case when we have a discrete time parameter set and we have a discrete state space or countable state space. Okay, so we will construct as a probability space that carries the process the canonical pulse space, which is just the Cartesian product to the power of the cardinality of the index set, time index set. So it's just a collection of all functions which map the time parameter set into the state space. Each such a function is called a trajectory. And then we have the evaluation map for each I in the parameter set. We have to have the evaluation map of a trajectory. Namely, if we have one trajectory, then the PI map is just the evaluation of the trajectory at this time point I. Now we want to construct, as usual, something like a pre-measure on a properly chosen algebra of sets, and then we want to use the Karateodori extension theorem. And so let's choose the algebra of sets. That will be again our algebra of cylinder functions, which are generated as pre-images of finitely many countable subsets under these projections. Namely, if we fix a certain finite number of time points and a certain corresponding finite number of subsets, measurable subsets in the state space, then we define a preliminary set function which will turn out to be a pre-measure on the associated cylinder set, which will be just the intersection of all the pre-images of these window sets on the full trajectory space by the following seemingly complicated formula, which I probably will not discuss here too much, because you just have to look at it and swallow it for a while. But if you look at it closer, let me give it a try, you will see, for instance, the formula that I shall write here now is a nested integral, which involves iterated applications of these transition functions to indicator functions of the corresponding sets through which you would want to go. So the whole thing, in the end, the outermost integration is an outermost integration with respect to the designated starting measure mu dx. And then what does it do? So then it does a step, if you like, from x. It says, okay, in one time step, I need to take a time transition, which is the corresponding time step from time 0 to the first time. I have to make a transition from my starting position into the set AI. But then these sequence of conditions which are encoded in this cylinder set, of course, determine a sequence of windows and time points through which, at which the trajectory has to go through those windows. And therefore, it's better to effectively understand this formula and to read it in reverse order. So if you look at this relation, so this here relation here determines a function, or this describes the probability to make a transition in the time step on the time interval from in minus 1 to in, to make a transition from wherever, which is a hidden variable here, into the set an, which is the latest window through which we would want to go. And of course, this, if I evaluate this with respect to all starting positions at time n minus 1, I need to integrate this only for all those positions at time point in minus 1, which are lying inside the set an minus 1, in the window which belongs to this time point one time before. So I need to integrate this with the indicator, because else I will not have any contribution to this probability. And that needs to be averaged with the possibilities of visiting a time point, a position in the set an minus 2 at time point n minus 2, and so forth. So in fact here I have to write, if I want to continue this chain of operations, I would have to write an in minus 2 in minus 1 minus in minus 2, and so forth. So I get this hierarchy of nested evaluations of these transition kernels, and I recommend that you write down this expression for 2 time points in order to see the nature. Now the semigroup property will allow you to conclude that this number, which we have defined through these nested integrals, will not depend on the particular representation of the cylindrical set. Recall that a cylindrical set has various representations. It's not unique, because you can always smuggle in an inverse projection of the entire set, of the entire state space E at any intermediate point, which gives an abundance of various but equivalent representations of the cylindrical set. But if you have more time points of evaluations, you would need to have more PIs here inside. But by the semigroup property, this would mean that, since these would involve integrations over the entire set E, such intertwined conditions would lead to additional integrations of semigroup evaluations at intermediate times, but then over the whole state space E, which by the semigroup property would basically cancel out, and you could just fill in the compressed expectation again. So therefore, this definition of a number for the cylindrical set is independent of the precise representation of the cylindrical set, and it gives a properly defined set function on this algebra. It's an exercise to show that this is that this is finitely additive on this algebra of cylindrical sets. And then you have to invest a little through a topological argument that this is in fact a pre-measure. Here is some work to be done. I will not present the full details of this because it's kind of technical, but here we are heavily dependent on the assumption that the space on which we work is in fact Polish. Okay, but on Polish spaces, this whole thing, this whole construction goes through. We can find that this is in fact not only a content, but it's actually a pre-measure on this algebra, and so therefore we can invoke Kara-Theodori extension theorem to show that there is a unique extension of this pre-measure to a measure on the Borel sigma field, which is generated by these cylindrical sets, and that's in fact the set on which we want to work. So we have a probability measure, which then shall be called P, or which is defined on this full path space equipped with the cylindrical sigma algebra. And we can see that we have random variables. We can now define random variables on this path space, which are exactly induced by this family of evaluation maps. And then we can convince ourselves easily that the finite dimensional distributions of this stochastic process are determined by exactly this formula, which was our defining formula or constructive formula for the definition of this pre-measure. And we can also see exactly by this formula that the transition statistics, or that this is in fact a Markov process, which is associated with exactly this transition function. So that was a very quick presentation of a very kind of complicated construction in the end, which involves quite a bit of measure theory. But the base message is, or the takeaway message is, that if you have a family of a transition family, or even a time homogeneous semigroup of kernels, which are defined on a Polish space, then given a certain initial probability measure mu, which is a starting measure for the process, then there exists a stochastic process, which is then a Markov process, which is time homogeneous and whose finite dimensional distributions are exactly described through this transition kernel or transition function, or in other ways, we have exactly a time homogeneous Markov process, which is associated exactly with these transition kernels, or with transition function. So, if you recall, in the first lecture, in a way, we were discussing that a Markov process gives rise to a transition function. And here the message is, okay, a transition function gives rise to a Markov process. So therefore, up to certain technicalities, which involve the question to what extent the semigroup property with respect to convolutions is actually true in a pointwise sense, or almost surely, modulo such technicalities, we can conclude that in terms of its statistical behavior, a Markov process in, say, continuous time is, if it is time homogeneous, is completely described by its transition function, which is a family of Markov kernels which satisfy the convolution stability property. Okay, now since we have basically clarified the connection between transition functions or semigroups of kernels and Markov processes in continuous time, we are left with the question, how do we characterize and how do we construct such semigroups of kernels? And that will now be the next step. We want to characterize and construct semigroups of kernels by analytic means. And that now is the place where a little bit of functional analysis enters the picture. Okay, we will work now typically on topological state spaces. In fact, we were doing it already before when we were talking about Polish spaces, because the notion of a Polish space is in fact based on an underlying topological structure, but it wasn't so obvious probably before. But now we will really confine the discussion to the case when the state space is not just an arbitrary measurable space, but it shall be a topological space in the future. But in most of the cases, of course, it will be basically the Euclidean space or a subset of the Euclidean space. So let E and tau be a space E or set E equipped with a topology. Then we can talk about the continuous functions on that space, and we can even talk about the continuous functions which vanish at infinity. And that is to be understood as follows. So a function is said to be continuous and vanishing at infinity if, first of all, it's continuous, and secondly, that for all positive epsilon we find a compact subset such that outside the compact subset the function f assumes values which are no bigger than epsilon in absolute value. So this says that if you like, outside of compact subsets, you can make the function arbitrarily small, provided you choose the compact set big enough. This is a way to say that the function converges to zero when you tend to infinity in this set E, but you're tending to infinity means that you lie outside of an arbitrarily or sufficiently large chosen compact subset. Okay, so therefore we call the functions which lie in the set of functions, or the functions which vanish at infinity. And then it's an exercise to show that if we equip this collection of functions with the supremum norm, that this again is a Banach space. So in a way, it's, if you like, it's a subset of the bounded measurable functions, but it is a closed subset of this, and it's therefore also a Banach space. Now comes an important definition, namely the definition of a Feller semigroup of kernels. Namely, let E be such a topological space, and we shall most of the time assume that this is a Polish space. Then we consider a family of continuous operators on this just introduced set of functions vanishing at infinity. Then we call this family of operators a Feller semigroup. That will be an important notion in the future. So we call this family of operators a Feller semigroup if it enjoys the following four properties. But before I explain those four properties, I want to give you an example, or I want to give you an example of what you should think about. So think about, for instance, Brownian motion on the Euclidean space. Then we can consider as a TS operation just the expectation of the function evaluated at a Brownian motion at time s when the Brownian motion was started at time 0 at position x. This is nothing but integrating out this function against the Gaussian density, which has properly chosen parameters. In this case, the center of this Gaussian distribution is just the x variable, which is the starting point for this Brownian motion, and the variance scaling parameter s is just exactly this s parameter, which stands for the time. So this operator as a function on functions is in fact a transformation of the function. So if we had a function before, which was called f, then varying over these different starting points for the Brownian motion, we get a new function, which is something like the average evaluation of the function f under a Brownian motion, which was started at a previous time at a certain location x. So this is the archetypical example of the type of operations that we want to consider. It will turn out that this operation here for the Brownian motion, of course, will be one example of such a Feller semigroup. But we want to go back now to the general case and want to introduce the general definition of a Feller semigroup. So suppose, again, let me say it again, we are starting out with a topological space which is assumed at the moment to be Polish. Probably this can be generalized to general topological spaces, but let's be a little cautious. So let's assume we have a Polish topological space, and assume we consider now the set of functions on this topological space which vanish at infinity. Then we furthermore want to assume that we're having a family of operators, of continuous operators, Ts, which are indexed here by the non-negative real axis as time parameters. Then we want to call this family of operators a Feller semigroup, named after the American mathematician Feller of the 20th century, if it enjoys this operation, or this family of operations enjoys the following properties, namely, if the function which is inserted into this operation at any time is positive, then the resulting function is positive. If you think of this example, that's the case. So this Feller semigroup, or these operators, should all convert positive functions into positive functions. That's condition number one. Second condition, if this family of operators evaluated at time s equals 0 is just the identity operator. So that would correspond to evaluating this Brownian motion at initial time s equals naught. Then the Brownian motion didn't have any time to go anywhere, and therefore this average evaluation is just the evaluation of the function f at the starting point, which corresponds to saying that the time equals 0 operation is just the identity operation on functions. Finally, we want that they have this characteristic semigroup property, which we had just discussed in the previous case. Namely, if I iterate this operation for two different, or same for two time points, then it's just the same as if I do an operation once, but with the time that is obtained by summing the two previous time points. This is exactly the semigroup property, which justifies why we're talking about the semigroup here in this case. And finally, we want that this semigroup is continuous in the following sense, that we want that if we send t to 0 and we evaluate or we apply this semigroup operation to a function and we compare to the unperturbed function, to the function which was not changed, then we want that in the supremum norm we have convergence to 0 for all functions in this set of functions which are vanishing at infinity. If these four conditions are satisfied, then I call this semigroup, or this family of operators, I call them a Feller semigroup. And this Feller semigroup is called conservative if, moreover, the constant 1 function is 1. Yes, then we should call this a conservative, then we should call this function, or this Feller semigroup, conservative. There's a little bit of explanation needed here, and this is why I was hesitating for a while, because typically, or if the space E, or the set E itself, is not compact, then the constant function, of course, is not vanishing at infinity. And then in this case, this has to be understood that there is an approximation, which is a pointwise approximation from below to the constant function 1 by functions which are vanishing at infinity. You can think of indicator functions of larger and larger balls, which are smoothened a little bit, such that this equality is correct in the end after approximation. Okay, if that's the case, then I shall call this semigroup conservative. So this here is an abstract analytic concept, and it seems to mirror these operations that we are familiar with from the example of Brownian motion. And I will give examples that there's generalizations of this, and this seems to generalize this, and it's not at this moment clear what this could have to do with the Markov process. But it turns out that such a Feller semigroup is the analytic description of a Markov process. And this is the contents of the next proposition, which is actually quite easy to show. And it says like this: so if we are in fact on a Polish space, and if we have a conservative Feller semigroup in the definition, in the sense of the definition above, then there exists a unique transition function pt on E, such that this corresponding abstract operator, which we had considered in this definition of a Feller semigroup, such that this abstract operator is in fact represented through exactly the operation of transforming a function by such a transition kernel. So in other words, transition kernels and Feller semigroups are the same, at least if these transition kernels enjoy the property that make the family T Feller. Or let me be a little more precise. It says that if we do have a a family of operators on function spaces which are a semigroup and which satisfy these Feller conditions, then there exists a unique transition function such that these abstract operators can in fact be represented as appropriate mean value operations by means of this transition function. And the upshot of this is, if you give me a Feller semigroup of operators, then I can construct an associated Markov process. Okay, let's prove this proposition. The proposition here is, again, effectively an analytic statement. It says that this family of operators, if it satisfies the Feller property, corresponds to a transition function. Before, we have already seen that a transition function induces a family of operators. And now we want to go the other way around. Effectively, we want to say that a family of operators, provided it satisfies certain structural conditions, gives rise to a transition function and therefore gives rise to a Markov process. Okay, let's prove here that this family of operators must give rise to this family of kernels. So by assumption, we know that this operation that takes a function and returns the operator at time t for the function, that this is a positive linear map. So it's positive by definition 0, by property 0, and it's linear. And then there is a theorem from measure theory of functional analysis which tells me that every positive linear map on the set of functions which vanish at infinity, for instance, every such a positive linear map is represented by a measure. So if we fix x, which is the case in our argument here, so first of all let us fix x, then this operation which takes f and returns the operation, the TT operator on f evaluated at x, then this is a positive linear map, and therefore we know that there is a certain measure which carries the index x and the index t for the time, such that this operation can in fact be represented by an integration against this properly chosen measure. That's an application of the Ries representation theorem, which tells us that the dual space of bounded continuous functions are this set of measures. Okay, now what we also know is that if we now fix this measure for all x, then this operation that takes x into this integral, which is just the evaluation of which is just the application of the TT operator to the function f, this returns a continuous function. So therefore, this is a Borel measurable function in particular, because continuous functions are measurable. Now we want to conclude that this family of kernels, at least for fixed t, is measurable with respect to with respect to x. That is what we would want to conclude, but that is a simple consequence of monotone convergence, if you like. If we replace, or if we want to evaluate the kernel at a fixed measure, at a fixed set A, we just would want to approximate the function, the indicator function of this set, by a monotone, if you like, approximation of the indicator function of the set by continuous functions, which is possible in particular in Polish spaces. So therefore, by some monotone convergence theorem, we can find that this function here as a function of x can be understood as the pointwise limit of the corresponding functions which are obtained by replacing f with an fk, and then we can see that this function here is a function which is obtained as a pointwise limit of continuous functions, so therefore it's in particular the pointwise limit of measurable functions and must be measurable. So therefore this operation is measurable with respect to x. In particular, for each t, this object as a function in x and a must be a Markov kernel. It satisfies these regularity conditions that we were imposing on transition kernels. Now, second, if we know that the transition functions t is conservative, then we find an approximation of the constant 1 function, which converges. We find an approximation of the constant 1 function, and we know that in the limit, this pt of 1 at x is a 1, which by monotone convergence, again inside this integral expectation, gives us the information that mu t x of the full set is 1. So hence we find that this mu t guy is in fact a Markov kernel. And what we also finally want to check is that we have this semigroup property of kernels, that these Markov kernels satisfy this convolution property, which by the way has the name of Kolmogorov. What is it again? I'm sorry, I need to think what's the name. Chapman-Kolmogorov equation. So this convolution property of kernels, which says that mu t convolved with mu s equals mu t plus s. This is also called the Chapman-Kolmogorov equation. So this is what we need to check only, which is left to check. So therefore we do this mu t plus s x at a. Again, if we choose some continuous functions which approximate, say, from above the indicator function of a, then by monotone convergence, this is the limit of these operations, and by the representation of this operator through this integral kernel, this is the limit when k tends to infinity of the application of the TTS operator to the function fk. Now by the semigroup property of these operators, we can also write this t at t plus s as a consecutive application of ts and then tt. Well, what is tt? We write the outer application of the ts operator, again by means of the integral kernel, which we had already constructed for the time parameter s, and that is then the kernel against which we integrate the inner function in order to represent this operation here. But now again by monotone convergence, I can pull this limit in k inside the integral. But I know what again by monotone convergence for the integral representation of the inner thing, I know that this converges for k to infinity to the corresponding measure of a under the kernel mu t. And hence I see that I have exactly this convolution equality that I was aiming at. So whenever these operators are a semigroup, then the corresponding representing kernels must necessarily satisfy this Chapman-Kolmogorov equation. And hence I concluded that this family of Markov kernels is a transition function on this set E together with its sigma field curly E. The uniqueness of this family of kernels is also a direct consequence of the way to represent the operator T by means of this kernel. As a remark, I would also like to point out that there is a version of this theorem under a weaker condition, which is the case when we do not ask for conservativity of the semigroup, but instead we ask for contraction. And this means that we ask that the application of the TT operator at any t gives a function whose supremum norm is no bigger than the initial function that we put into this operator. In this case, we will talk about a contraction semigroup, and that also allows to the similar construction as in the previous proposition, but we can no longer guarantee that the Markov kernel or these transition kernels that we construct will be probability preserving, which in particular means that the measure of the full set for any of those kernels is in general only bounded from above by 1. So it's a sub-probability measure, but we can basically build on our previous theorem by then considering the one-point compactification of our state space E, or by just associating another point to the state space, which is an additionally added point, which is sometimes called the cemetery. And then we can extend this sub-Markovian kernel to a kernel on the full space, which will then be really a probability kernel, by putting all the defect measure that is missing onto this artificial point delta. And then we obtain, in the end, a Markov process which assumes values in this extended space where this additional artificial point is considered what's called a cemetery, and it indicates the fact that the process has left the initial state space E and has assumed a value, this point delta, from which it will no longer return. So that would be the case of what is later called an explosion of the Markov process, which means that it leaves the initial set E in finite time with positive probability. But typically we will not have this case, this generalized case. Typically we will have a conservative case when it is not necessary to consider this additional point. But the theory still is extendable to such a situation. Okay, so what have we learned so far? We have learned that the Markov process gives rise to a family of kernels through the operation of taking the conditional regular expectation, and this family of kernels does satisfy these Chapman-Kolmogorov equations, at least on those points which are actually visited by the Markov process. On the other hand, we have seen that if we have a transition function, such a family of kernels, which satisfy this Chapman-Kolmogorov equation everywhere, then we can construct out of this a Markov process. We have seen that if we have a family of operators on the space of continuous functions which vanish at infinity, which satisfy these Feller conditions on this property, on these Feller conditions on these operators, then we can associate to this a family of kernels from which we can construct a Markov process. So therefore, in a way, we have now completed a picture which basically says that semigroups of operators are in a one-to-one correspondence to Markov processes, modulo certain technical details related mostly to the validity of these Chapman-Kolmogorov equations in every point. And for that purpose, we introduce the following notation, which says that the transition function, so that's the analytic object, let me say it again, the transition function is the family of kernels satisfying the Chapman-Kolmogorov equation. A transition function associated to a Feller semigroup. So if we starting with a transition function, and we find out that if we write down the corresponding family of operators, then this, and if it is the case that this family of operators satisfies the conditions for a Feller semigroup, then this whole transition function is called a Feller transition function. And a Markov process, which is associated to such a Feller transition function, is then ultimately called a Feller process. It turns out that you can derive further regularity properties for a general Markov process which satisfies the additional Feller conditions, but we will not invest too much in these additional regularity properties, because in our investigation we will use the analytic theory to study a Markov process whose regularity properties are typically not the central issue. Typically we will have Markov processes or just basically solutions of stochastic differential equations, which we then a posteriori will be identified as Feller processes, but for which we have regularity properties just from the fact that they are solutions of certain stochastic differential equations. Okay, we will not therefore pursue the abstract theory of pathwise regularity of Feller processes, which is a theory of its own. But we will now we'll come back to this example that we study most of the time, at least in this introductory part of the lecture. So again, let us consider the example of the Brownian motion semigroup or Gaussian semigroup, of which we know that the application of the semigroup to the function f is obtained by applying the Gaussian kernel or integrating against the function f against the Gaussian kernel, which is properly shifted in space. This is the spatial shift by the position x, and which is properly scaled with respect to time to account for the time parameter. So this x parameter is here the additive shift by which we move the center of the Gaussian, and the t variable stands for the variance of the Brownian motion at time t. And this can also be expressed as we had done now a couple of times already. This can also be expressed in a probabilistic fashion as the expectation of the function f when it is evaluated at a scaled and shifted version of a standard Gaussian variable. Namely, we scale a standard Gaussian by square root of t in order to produce variance t, and then we shift it by an additive shift towards to be centered at x. So these two things are obviously the same, and we can see directly that this operation is a Feller semigroup. Why is this the case? Well, the convolution property, that is something that we have checked already a couple of times by now, in particular in the last exercise. And the important question that we need to check is whether this operation, if we insert or if we apply it to a continuous function, which vanishes at infinity, whether this new function as a function of x, so after we do the integration, we are left with a function which is dependent on the x position, and then we can check whether this new function is in fact a function which is continuous with respect to the x parameter. But that's a straightforward application of dominated convergence, for instance, and whether that vanishes at infinity. But again, for continuity, so suppose you have a collection of, or you have a sequence of x points that converge to x, and you ask for the convergence of the corresponding expressions with respect to xk, then again, just by continuity of the f function, pointwise we have pointwise convergence of these expressions to the expressions inside the expectation, and then by dominated convergence, since f is a bounded function, it will converge. And it's also an easy exercise to see that this function f will vanish at infinity. Okay, so therefore the Gaussian or Brownian semigroup, which comes with the Brownian motion, is a Feller semigroup in the sense of the definition above. So we have just completed a broader picture which tells us that the statistical description of a Markov process is equivalent to knowing an associated semigroup of operators which satisfy certain structural conditions. And therefore, we can ask ourselves, how do we actually construct such appropriate semigroups of operators that ultimately give rise to Markov processes? And here is an important concept which basically brings about a condensed and super compact description of all the statistical information that is in a Markov process, and this is the concept of a generator. Before I introduce the concept of a generator through this definition, I would like to recall to you once more the analogy that we have with a one-dimensional classical exponential function, which also satisfies the rule that tt, if you call t the exponential function, that tt times ts equals t plus s. And we know from standard calculus that whenever we have a function on the real line that satisfies this functional equality, then this function must be of exponential type. So it is a function of the type, it's an e to the alpha t. And hence we know everything about the function once we know the alpha. And how do we get the alpha? One way to do that is to take the derivative of this semigroup or this function at time t equals 0, which will then recover the coefficient or the coefficient alpha, which is exactly the information we need to have a full description of this semigroup or of this function. And we shall do now very much the same thing, but in an infinite dimensional context, when this constant alpha is in fact not a constant, but is a linear operator. And that's exactly this linear operator, this alpha or a, as we shall call it, is then what we shall introduce as the generator of this semigroup. The definition goes like this. So let X be a Feller process on a topological space. And I should probably emphasize here as a side remark that whenever we do not refer to constructive things in measure theory, we it is typically sufficient to assume only that the underlying space is a topological space. It's not necessarily a polar space, but that's just a side remark. So let X be a Feller process on a topological space such that the associated Feller semigroup has, in fact, the Feller property as a semigroup, and which then shall be denoted PT. Then we shall introduce now the so-called generator of this process, which is defined as follows. Given a function f from the collection of continuous functions vanishing at infinity, we say that this function has the additional property that it belongs to a particularly good set, namely to the domain of the to-be-defined operator A, if the following limit exists. Namely, if we apply the semigroup to the function to yield a new function, from that we subtract the unperturbed function, the initial function, and we divide the whole thing by t and let t tend to 0. If that limit as a limit of functions in the space of vanishing, of continuous functions vanishing at infinity, if that limit exists as a limit with respect to the topology of uniform convergence, then we say that this function belongs to the domain A to dA, the domain of definition of the operator A. And in this case, the operator A is in fact defined to be the limit. This defines the generator of a semigroup, or the generator of a Feller semigroup in this particular case. And we shall argue below that this generator contains all the information we need to have a full description and a full recovery of the semigroup. Hence, this operator is a supercondensed description of the statistics of the process. And in a way, we do not need anything else except this analytical information in order to describe the process. Okay, we shall further down below extend and explain why this process, or why this generator is so important. But before we develop further theory, we want to give an example. Namely, of course, we will pursue the example of Brownian motion, standard Brownian motion on Euclidean space, which, as we had already seen, gives rise to a Feller semigroup. And we claim now that the generator for this particular Feller semigroup, which comes with standard Brownian motion or Brownian motion on one-dimensional Euclidean space, is described as follows. The domain of the operator, which we will introduce, is the function C2R, and here I should change the notation. I did inconsistent notation. My notation for that space should be like this. So I consider the function, the collection of functions which are twice continuously differentiable on the real line, such that the function itself, the first derivative and the second derivative functions, are all functions which vanish at infinity. I claim that this is the domain of the generator of Brownian motion in the sense as defined above. I shall denote this space in the future as with this notation. It's a C superindex 2 subindex 0, 2 for twice continuously differentiable, and 0 for the requirement that all these functions, the function itself, its first and its second derivative, are functions which vanish at infinity. And in this case, the generator applied to such a function is the new function which is 1/2 the second derivative of the initial function. So you see that this is an operator which takes as an input a certain function, a continuous function with additional properties, and it returns a continuous function. So therefore it's an operator which maps this subset dA, which is a subset of all continuous functions vanishing at infinity, into another function which will be a continuous function vanishing at infinity. Okay, we want to show that in the sense of the definition above, The Feller semigroup, which is associated to Brownian motion on the Euclidean space, is in fact this operator. And we shall do this in two steps. We shall first show that whenever we have a function which is in this subspace of all functions, continuous functions which vanish at infinity, so if we do have a function f, which is not only vanishing at infinity and continuous, but is also vanishing at infinity and continues together with its first and second derivative, then we want to show that this function is in the domain of the generator and that the generator is exactly this operator. This is what we shall do first. This will be the end of today's session, and then we will add a little bit of abstract theory on semigroups before we come back to the proof and show the other implication or the other subset inequality, which says that if a function is in the domain of the generator, then in fact it must belong to this subset on the space of all continuous functions. Okay, so I want to show that if we have a function which is in this subset of even nicer continuous functions, then this function is in fact in the domain of the generator of Brownian motion, and the generator of Brownian motion applied to such a function yields this function back. Okay, for that purpose we have to consider this discrete or this approximation of the differential at zero of the semigroup applied to the function. For that purpose we need to evaluate the semigroup for Brownian motion on the function and at a certain point x. Well, we know that this allows for this representation through a standard or through an evaluation of a function on a shifted and scaled standard normal. Hence, if we consider the difference of the function itself together with the perturbation by the semigroup, we can pull in, if you want, this constant with regards to the expectation inside the expectation, such that we have this difference inside the expectation. And then we can use the fact that the function f is C2 regular, which allows us to use a Taylor expansion with the error term given by Lagrange, if you like. So therefore this difference can be expressed in terms of a Taylor expansion of order 2. So therefore it's the f prime, the first derivative at x, multiplied by the difference between the two arguments, which is square root of t times psi, plus 1/2 the second derivative of f, evaluated at a certain theta, which is in the interval between x and x plus square root of t psi. So this theta will depend on x and psi, on the realization on x and the realization of the psi random variable. So that's the theta here, times the difference between the two arguments squared with the 1/2 factor in front, of course. Okay, here it's written again. So this theta is some point which lies in the interval between x and x plus t, squared t times psi. This is correct if psi happens to assume a positive number. If not, if its psi is negative, then of course we have to write that this theta needs to be in the set x plus square root of t psi x when psi happens to be negative. Psi is a Gaussian random variable, so it can assume positive and negative values, and therefore it is this theta is in one of the two intervals, or is in that interval, but we have to write it properly depending on the sign of psi. Okay, so we have this representation for this difference by means of a Taylor expansion. And inside the expectation, we see that we have a sum of two terms. Of course, the sum of two, this expectation of a sum is a sum of expectations, where we see that if we consider the first summand here, the only dependence we have on the psi variable is exactly the psi variable alone, and we have a certain deterministic prefactor, which is deterministic for this expectation, which we can pull outside the expectation. So this constant can be pulled outside this first expectation. And what we are left with in the first summand is just the expectation of psi, but psi is a random variable with expectation 0, so therefore that term will not show up. So as a matter of fact, we only have, since this first expectation vanishes, we have only the second expectation. And for the second expectation inside, we just add and subtract a 0, or we add a 0 by adding and subtracting inside a deterministic number, which is just 1/2 t times f double prime of x. And of course, we have to correct this by putting in this f double prime of x. And here's a misprint again, apologize. Here, of course, we have the f double prime of x, which we put in and outside. So that's what we got. Hence, if we, and also we should probably point out that the square root of teeth guy, which we had in the difference of the two positions in which we evaluate the f function, now through by the Taylor expansion, of course, appears as a plain t in front, because we are dealing here with the second order expansion, which leads to a squaring of this term. Okay, so hence, if we put this back into the formula for this difference quotient, we have to take this difference, which we have just evaluated, and we have to divide by t. And we see that what we're left with is 1/2 f double prime of x plus minus, depending on how you want to write it, the remainder term. I prefer to write it plus, in fact, plus the remainder term, which has the representation that it is the expectation of f double prime at this intermediate point theta minus f again double prime at the position x, multiplied by xi squared, where xi is our standard normal with regards to which we do this expectation here inside. So in this last transformation of this difference quotient, we have already seen that this quantity that we conjecture is the generator of Brownian motion applied to the function f, that here it shows up already. So therefore I have an idea of what the limit of this difference quotient might be. We conjecture this is exactly the limit, so I subtract this suspected limit from the difference quotient, and I have for the convergence, which is required through in the definition of the generator, and the convergence is required to take place with respect to the supremum norm. So I take the supremum norm of this difference, and by the error term representation that I have just presented, this whole thing on the right hand side, if I take the supremum over all x, is bounded from above by the supremum over all x of this error term on the right hand side, which depends on x, where I have inserted the absolute value inside the integral. And now my job remains to show that this quantity on the right hand side is less or equal to epsilon for any epsilon, provided t is chosen smaller than some t naught of epsilon. That's the job to be done. If that can be achieved, then I have proved that in fact we have convergence of this difference quotient towards this quantity with regards to the supremum norm. Okay, you can convince yourself that as an exercise that a function which is continuous and vanishing at infinity is in particular uniformly continuous, and we shall use that a little later below. This means in particular that this evaluation of this second derivative at two different points will be smaller than any epsilon if the maximal difference between this psi and the x is smaller than a certain delta, but that can in particular be achieved if square root of t times psi is less or equal to delta, where psi is the realization of the Brownian, the realization of the Gaussian. And in order to use that uniform continuity inside this error term on the right hand side, I decompose this error term in order to have, on the one hand, uniform control on the size of this psi, of this perturbation value, and on the other hand, I try to find some other estimates which allows me to control the parts of the expectation when the psi variable assumes large values. For that purpose, I decompose this expectation into an expectation on two sub-events, namely the sub-event where the realization of the psi random variable is large, and the other complementary sub-event, which corresponds to the realizations of the psi random variable below a certain, in absolute value, below a certain number r, where r is a free parameter that I shall choose in a second. Now, for the first of these, that gives me a decomposition of this expected value into a sum of two quantities, which I shall estimate separately. For the first quantity, which is this expected value of this difference times psi squared and so forth, on the sub-event of large realizations of psi, I estimate this difference evaluations in absolute value by just 2 times the infinity norm of the second derivative, which is a finite quantity by assumption, and it remains as an upper bound the psi squared integrated over this sub-event, but this is small, arbitrarily small, for large enough r due to the uniform integrability of psi squared, of this Gaussian random variable. So this quantity here is altogether less than, so the first of the two quantities is less than epsilon half, if you like, for large enough r due to the uniform integrability of psi squared, and due to the fact that this is a finite number. Okay, that takes care of the first term. So I fix, I'm given a certain epsilon, I fix an r such that this whole thing here is smaller or equal to this epsilon over 2 for that particular value of r. Now the r is fixed, and I take a look at the second term, the second expectation, which is this evaluation of these differences of the f function on those realizations of the on the sub-event where the psi is in absolute value less or equal to r, but then the uniform integrability, the uniform continuity of the f double prime kicks in, which tells me that since psi is uniformly bound, this theta variable cannot be further away than square root of t times r from the x variable, and hence if I choose t small enough in order to have a difference of evaluations here no bigger than, say, r squared times this r times some epsilon half, then I find that this number here on the right hand side by uniform continuity is less or equal than epsilon half, and altogether I found a t which is sufficiently small, and for all smaller t, such that this error bound, or the error on the right hand side, which was this quantity here, this guy here is in fact smaller or equal to epsilon for all t less or equal than t naught of epsilon than t naught, which is exactly the statement that I was trying to obtain. So hence I find that if f, the function f, satisfies the regularity conditions as stated, in particular that the second derivative is bounded and vanishes to infinity, then this limit of this difference quotient exists with respect to the uniform topology, and the limit of this difference quotient, which then will be the generator applied to this function, is in fact the new function, which is the half of the second derivative of the initial function. This shows the first part of our proof, namely that the functions which have this regularity are in the domain of the generator, and the generator is exactly this half second order derivative. The other part, the other inclusion, which says that if a function is in the domain of the generator, then it must have this regularity properties, will be delivered in the next segment. But before we can deliver that, we will have to provide additional theory which will make it easier for us to prove that. That's actually not a so trivial proof and it requires, well, is facilitated by additional theory, which we shall present before. And as a final remark of today, and the corresponding statement for Brownian motion in dimension greater than 1. So if x is Brownian motion in t dimensions, then the corresponding generator will be the function space, a space of functions whose second order derivatives vanishes. And so it will be a function which is continuous, including its first two derivatives, and we also require that the first two derivatives are continuous functions which vanish at infinity. And then the generator on such a function will be 1/2 times the Laplacian operator of the function f, which is 1/2 times the sum of the second order derivatives. We have already seen in the previous semester that the Brownian motion and Laplacian operator have a very close relationship, and the theory that we shall see, and with that we are just that we are currently developing, exhibits even a closer connection. It tells us that all the information in a mathematically consistent and complete description of Brownian motion is already given by knowing the Laplace operator. That will become clearer in the course of the next few segments. And we will also, of course, study examples where the process is not just a plain Brownian motion.